Okay, so first of all, I would like to thank the organizers for the opportunity to speak, and for those of you who stick around after such a long day. Just in the beginning of the conference, Carlo Beinaker mentioned that the zero Landau level in graphene is not interesting. And I have to disagree with it completely. So I'm going to talk about the states that you can get at a zero filling quantum Hall regime in graphene. And in fact, there's a richness of many body states that you can get there. And the focus on my talk will be about how the edge modes can encode what's happening in the bulk states, and in particular, if there are different phases in the bulk, how it shows in the transport properties of the edge states. So this, the work that I'm going to summarize is in these three papers, the last of which just posted on the archive months ago, and my collaborators are Ganapati Murthy and Herb Fertig, and my student in Bar Ilan, Pasha Tikhonov. So this is the outline. So I will start with some very brief introduction to the nu equals zero quantum Hall state in graphene, and what is known about it theoretically and experimentally. In particular, its controversial transport properties. And then I will focus on quantum phase transitions that have been predicted to occur between two different magnetically ordered states at this state. And I will describe our theory, which essentially studies how the edge modes evolve throughout the transition, and how it affects the transport. So I apologize that I will not have time to give an extensive introduction to graphene. I'm sure Eva will do it tomorrow. But I want to stress that one of its unique features, if we look at the quantum Hall effect, is that it has a zero quantum Hall state at exactly zero, and this is unique. It has no analog in a standard 2D electron gas. And what you see here is the spectrum of Landau levels in a ribbon of graphene, plotted as a function of a guiding center. Indeed, there is a Landau level spectrum that includes an energy Landau level state at exactly zero energy. But there is a huge degeneracy, and in particular, there are internal degrees of freedom. There is the spin and the valley isospin, and various interactions and external fields can split them, and the unique feature of the zero Landau level is that because it's inherently particle Hall symmetric, every time you split some internal degree of freedom, it always splits to pairs of particle and Hall symmetric states. So in particular, if you have a ribbon with an edge, on the edge, the valley degree of freedom is split, and then you get particle and Hall-like states, which disperse like this. Now, this has assumed that I'm completely ignoring the real spin degree of freedom. But if we zoom in and assume that there is some Zeeman splitting, and all it does is just to split the spectrum to spin up and down, we find that at exactly zero energy, there is a crossing point in the non-interacting electron spectrum between right movers with spin up and left movers with spin down. Namely, we get helical edge modes, just like in the edge states of a 2D topological insulator. And about 10 years ago, it was actually suggested by Abanin, Lee, and Levitov to be a realization of the quantum spin Hall effect, but of course in a strong magnetic field. So this is a non-interacting picture, and there is, however, something we have to worry about it. The Zeeman energy is really tiny, especially compared to the typical scale for a Coulomb interaction. It's 2 orders of magnitude smaller. And we might want to ask, what would the interaction do? And in fact, what one expects, at least at first sight, is that interaction will turn the bulk state into a ferromagnet. So in fact, it introduces some exchange energy, which stabilizes the spin polarized state by interaction, by exchange interaction. And then the bulk will be now a quantum Hall ferromagnet. But on the edge, this kind of edge structure that you get from the non-interacting picture is not favorable, because the exchange energy does not allow a sharp flip of the spin. So instead, you're going to get a domain wall, which changes smoothly over a very large distance compared to the magnetic length. And in the middle of the domain wall, there is a spin that polarizes in the plane perpendicular to the external field. And in fact, it can freely rotate in plane. And thus, you get some collective mode, which is gapless, and it can conduct charge. And in fact, all that happens, all that the interactions do, is to turn the helical non-interacting edge mode to a helical Lattinger liquid. It's still a one-dimensional mode that has this helicity property, namely the electric current is enslaved to the spin component SZ. And you can easily generate a collective excitation, which corresponds to a smooth spin wave with some planar twist, which transfers charges over the edge without cost of energy, or with very small energy. So basically, if to summarize what I told you so far, we expect the nu equal quantum Hall state to be essentially very similar to usual quantum Hall plateau states. Namely, it's going to have a plateau at sigma xy equals 0, because there is a gap in the bulk, the Zeeman gap, or the exchange energy gap. And because of the helicity, it's going to be relatively immune to backscattering. And then the conductance will be maybe not perfect, but at least you expect to have some dip in the resistance at zero filling. And so it should be a good conductor. And however, and let's now go to the experiment, and that's not what you see. It was a bit controversial in the beginning when it was observed that indeed when you apply a sufficiently strong magnetic field, a plateau opens in sigma xy at 0, but the longitudinal resistance does not vanish or show a dip. On the contrary, it shows a peak at nu equals 0, and in fact it's insulating. And that is, I think, agreed by almost all the group that observe it. So something was missing in the theoretical picture I mentioned before. And what was missing is that we forgot, or we have to pay attention, that in graphene, you don't have only one spin degree of freedom. There is, in fact, also the valley. And altogether, you have an SU4 symmetry group that can be broken by interactions in many different ways. So it's much richer than the SU2 case, and you can get a variety of phases. It was discussed by quite a few papers. I don't cite all of them. And in particular, there is a work by Maxim Kharitonov that predicted a rich phase diagram, and one of the phases that appears to be most consistent with realistic parameters is a phase that tends to be anti-ferromagnetic, not ferromagnetic, but because of the external field that induces a Zeeman energy, a Zeeman field, there is a slight canting, and the canting angle depends on the Zeeman energy. And when you increase it, if you could increase the Zeeman energy independently from the magnetic length, then there should be a critical point where there is a second-order quantum phase transition to a ferromagnet. So, and then the ferromagnet should behave as we said before. So, indeed, there is some very nice experimental data of the MIT group. The first author is Andrea Young. And what they did is they put their graphene sample in a tilted magnetic field, so you can control the Zeeman energy independently from the orbital degree of freedom. And they saw that when you increase the tilt angle or the total magnetic field, the conductance, two-terminal conductance, changes from 0 to a plateau that is close to, but slightly below, the perfect conductance of 2e squared over h. So this appears to be consistent with this picture. However, if you look at the transport data, it's very hard to place here where is the transition, because it all evolves very smoothly. And in fact, there's a lot of structure. And
why do you expect a phase transition? Why wouldn't it be smooth?
No, so in the bulk, if you write a model for an anti-ferromagnet with some orienting magnetic field, there is a second-order phase transition. It's well studied. Okay, that's in the bulk. Okay, but what you see in the transport does not reflect something very sharp, and it has to do with the fact that the edge states evolve in some way, and this is exactly what we have been studying. So first of all, before I will not go to any details of the theory, but the first stage is to see what is the ground state of a system when you account for interactions and the Zeeman energy and, most importantly, an edge potential. So basically, the first stage was to repeat Kharitonov's calculation, which is basically Hartree-Fock, a mean field, but with an edge. And just like in Kharitonov's model, we assume that in addition to the Coulomb interaction, there's a short-range interaction, and that's very important because that's a term that is something that there's some lattice scale interaction that knows about the orbitals, and that can break the SU4 symmetry. Okay, and that's the reason why you favor in the first place the anti-ferromagnet and all that. So. And we put an edge potential in terms of something that splits the isospin, and just find what is the ground state when the 0 Landau level is half filled, namely the chemical potential is exactly at 0 energy. So this is what we found, that you can characterize the ground state basically by two generalized spinors that evolve smoothly towards the edge. And these spinors can be described by two canting angles. So there are, in fact, two distinct canting angles that rotate the spin in this SU4 manifold. The spinors have some entangled spin and valley configuration. So for arbitrary canting angles, they don't have a well-defined spin or valley. It's some linear combination. And what I plot here is these canting angles. One is the extended line and the other is the dotted line as a function of the guiding center, where this is the edge on the right. So these were found for the canted antiferromagnet phase, and this is for the ferromagnet. And in fact, you see that they look very similar. But there is a very subtle difference between the two phases. The subtle difference is that only in the ferromagnet, the spin configuration changes near the edge from 0 to pi. The canting angle changes from 0 to pi. So in fact, this allows you to generate excitations, collective excitations that have a topological charge, and that topological charge is what carries the electric charge in the quantum Hall system. Now, another point that I want to make, I want you to note is that there is some natural length scale that appears here that has nothing to do with the edge potential. The edge potential is assumed to be very sharp. So there is a diverging length scale that comes from the bulk transition. It's something that diverges near the transition, the second order bulk transition. And that length scale determines the width of the edge domain wall. So as we approach the transition, the edge becomes fatter and fatter. In fact, in a sense, at the transition, there is no distinction between the bulk and edge. So now we are ready to discuss the excitations. So far, I just told you how the ground state look like, but the modes that can carry charge or spin in this system are fluctuations above the quantum fluctuations of the ground state. You can characterize them in terms of fluctuations in the, sorry, is this working? You can characterize them as fluctuations which involve rotations of the spins in the plane and fluctuations in the amplitude, and there are some non-computing operators associated with them. And without getting into details, let me just summarize what you find. So first, look at the collective charge excitation. The charge excitations are the objects that can carry electric transport and participate in the conduction. In the canted antiferromagnet, and as I said before, in the quantum Hall regime, in order to generate a charge, the charge always comes with a spin texture, with something that has a Berry's phase, or a Pontryagin number. And in the case of the canted antiferromagnet, we can generate such an excitation. So of course, we can generate such excitations in the bulk, which are going to be some kind of skyrmions, but they're going to be gapped. But the lowest energy excitations you can make are on the edge. So we take advantage of the fact that the domain wall already gives some twist, but it's not enough to generate a charge excitation. We have to bind it with some bulk texture. That's a meron. It's half a skyrmion. And you can think of the edge mode as some kind of a bimeron excitation, which has a finite extent, and it turns out that it has a gap. And this object will evolve in the ferromagnetic phase to what I told you in the beginning of my talk, which is a twist that occurs only on the domain wall and costs no energy. So the gap, so in the canted antiferromagnetic phase, you have a gap to this excitation, and the gap can be calculated for magnetic energy. Basically, the energy cost is magnetic stiffness that has to do with creating such a twist. And that's what we get. We get something that is dictated by the bulk stiffness to rotation in the plane, and it's vanishing at the transition and becoming gapless. So if I plot a diagram which describes the gap to charge excitations as a function of the Zeeman energy, when I go across the transition, there is some finite gap, it vanishes at the transition and becomes zero. Now, in addition to the charge excitation, we also have neutral excitations that are only spin waves. They are some kind of spin mode, and they also behave very differently in the two phases. In fact, if we look at the neutral excitations, which reside in the bulk, in the ferromagnet, you have spin wave excitations, but they have now a gap. And that gap, once again, goes like easy minus easy critical. So it goes to zero at the transition and vanish. And then at the canted antiferromagnet, there is a Goldstone mode, which is a gapless neutral spin wave mode with zero gap. So in a sense, there is some duality relation between the edge and the bulk and the charge and the neutral excitations, where the charge excitations are gapless in the ferromagnet, and the neutral excitations are gapless in the canted phase. Okay, so now let me discuss the transport. How much time? 5 minutes? Okay, so I want now to discuss why there is a deviation from a perfect conduction, right? I mean, this conductance plateau doesn't reach 2. And the first question to ask is, what will dominate? Why, first of all, we expect to get a perfect conductance? Let me remind you. So the correction to the perfect conductance is related to the dissipative resistivity, which can be expressed as some relaxation, in terms of some relaxation rate of the electric current. Okay, so in fact, it's like there's some inverse Kubo formula, like things that you can write for it. And the problem is, remember, we are discussing a helical edge mode, and the helicity is encoded by the fact that the electric current is enslaved to the spin component SZ. So as long as SZ is conserved, this process of backscattering is forbidden, and since the SZ is conserved, JE is conserved, the time derivative is 0, and the current cannot relax. So basically, this is one way of seeing it. There's nothing to relax the electric current unless we can somehow flip the spin. But there is something that can flip the spin, and that's, if we forget about extrinsic effect, these are the spin waves in the bulk. And indeed, they are gapped, but the gap is small, and in fact, it goes to 0 close to the transition. So you can have, once I account for the fact that there are some spin waves, they assist in the flipping of the spin, relaxing it to the bulk. And then if you introduce some impurities, even without impurities, but definitely with impurities and the spin waves combined, you get some relaxation. So I don't want to discuss too much equations, but we have some effective model for the system edge and bulk, which can be implemented to calculate the transport. And the one important thing I want to stress is that all the parameters of the model encode the proximity to the phase transition. So there is some energy scale that goes to 0, and that's the thing that makes all the parameters encoding the critical properties of the bulk, essentially. So here is a result. We get some scaling formula for the resistance as a function of temperature, and delta, where delta describes the proximity to the transition, EZ minus EZ critical. If we look at, we compare it to the experiment, we didn't try to do any quantitative fit because there's not enough data to compare to, but you can see that if I look at finite but low temperature and look at what happens as a function of EZ, like what they did in the experiment, it appears like an apparent saturation. So qualitatively, this gives the correct behavior, which you observe experimentally. So let me summarize. I argue that in the mu equal 0 quantum Hall state in graphene, the transport is dominated by collective edge modes. There are in fact, some kind of spin waves that carry charge, but couple also to spin waves in the bulk that control their transport properties. These collective edge modes, they live or they attach to domain walls in the spin configuration near the edge. They have an effective width which diverges near the transition, and this is, by the way, something that would be very nice to see in some experiment that can measure where the current flow. So just for all of the people here who do scanning of various kinds. And finally, about the transport, I discussed a transition between two distinct phases that have different magnetic order in them, a canted antiferromagnet and a ferromagnet, and they have radically different transport behavior, but moreover, in some sense, the two phases are dual to each other. In one of them, we will get an exponentially small conductance controlled by a charge gap, but the charge gap, the energy of it is magnetic in origin. It has to do with magnetic stiffness. And in the ferromagnetic phase, we get an almost perfect conduction with corrections that at low temperatures are expected to be exponentially small. And there's an energy gap in both phases that goes to 0 at the transition. So thank you for the attention. Yeah?
Why is the full symmetry SU4 rather than just SU2 plus SU2?
Because there is, because it doesn't, you have in fact 4 states that you can build in this, if you like, in this manifold, and they're all equivalent. So there's nothing that breaks it. Of course, you can introduce, and that's indeed what happens. If you introduce some interaction, it can have anisotropy in only the isospin or only the spin. But just to start with, the full symmetry is SU4.
So do you have a proposal for experimentalists? Can one see these merons?
Okay, yeah, so that it would be really nice. I mean, in principle, you should be able to see if it's static. Let me put it this way: if they are pinned, if this is a static object, you should be able to see it in scanning in some way because it's a spin texture.
So you
Right.
have single spin sensitivity.
But it's not single spin. It's an extended object. So I don't know if it's possible to access in any way directly. I think that one thing that really would be nice, it may be a very difficult experiment, but to see this divergence of the width of the channel, that could be something that should have dramatic, that should be relatively easy to access if you can, for example, do what Amir Yacobi does, and Moshe Ben Shalom, in fact, which is a Josephson Fraunhofer pattern. But it would be very difficult because the whole experiment, the conditions for the experiment are very high magnetic field. Yeah. Okay.
If there are no more questions, let's thank Efrat again.